Hello everyone, this video is brought to you by the Atılım University Open Courseware project for Physics 101. In this video, we are going to solve some problems related to chapters 5 and 6, namely force and motion. Okay, shall we start? In this problem, we are given a three-dimensional block which is in the shape of rectangular prism, and it moves to the right on the two-dimensional plane-shaped surface. The coefficient of kinetic friction between the block and the surface, which is denoted by mu k, is equal to 0.4. The question is that if the mass of the object is 4 kg, find the magnitude and direction of the frictional force on the block from the surface. Before seeing the solution, please pause the video and try to solve it. Okay, let's start. First of all, we collect the known quantities, which are the coefficient of kinetic friction, that is mu k, being equal to 0.4, the mass of the block, which is denoted by m, being equal to 4 kg, and despite not given, generally we take the gravitational acceleration, that is g, as 9.80 meter per second squared, and it is in the downward direction. In the second step, we draw the free body diagram. We represent the block with a point-like particle, and the surface is represented by a straight dashed line. Then we draw all the external forces acting on the block. The first force is naturally the gravitational force, which is calculated as m times the acceleration vector g, and it is in the downward direction. The second force on the object is the normal force. Its magnitude is the magnitude of the net force in the perpendicular direction toward the surface, which is now in the downward direction. Here, the net force in the downward direction is only the gravitational force, which is acceleration vector g multiplied by the mass m. Then the magnitude of the normal force, which is denoted by capital N, is m times g. It is antiparallel to the net force in the downward direction, that is, the normal force is in the upward direction. We denote the magnitude of the kinetic friction by F sub k, where the subscript k is the abbreviation of the word kinetic, and it is calculated by the formula the coefficient of kinetic friction, that is mu k, times the magnitude of the normal force, which is capital N. Or, since n is m times g, then the formula is mu k times m times g. So, we put the values of these quantities into the corresponding places. 0.4 for mu k times 4 kg for m times 9.8 meter per second squared for g, which results in 15.7. Note that your final result has to be in 3 digits. Well, is this result true? No. The last step is to put the unit of the force, which is Newton, and it corresponds to kilogram times meter per second squared. Now we come to determine the direction of the frictional force. As you guess from your daily life experiences, it is antiparallel to the motion, that is, to the left. Okay then, we are done. Let's have a look at the second problem. In this problem, an upward force, as shown here, acts on a 4 kg object near the Earth. We are asked to find the magnitude and direction of the acceleration of the object when F equals 2 newtons, 20 newtons, and 200 newtons. First, we draw the free body diagram. The object is represented by a point. The external forces acting on the object are illustrated one by one. The natural force is the gravitational force due to the Earth, and it is in the downward direction, denoted by W. Since the object is near the ground, then we take the gravitational acceleration g as 9.80 meters per second square in the downward direction. Then W equals m times g. The other external force acting on the object is this upward force, denoted by F. Since there are no other forces acting on the object, we write the net force on the object. As seen from this figure, the motion will be in this straight line. The forces in this line are F and W. The difference of them, that is F minus W or F minus m times g, gives the net force on the object. To find the acceleration of the object, we make use of the Newton's second law, which is F net equals m times a. Here F net is F minus m times g. Then F minus m times g equals m times a. Dividing both sides by m, we obtain a formula for the acceleration a as a equals F over m minus g. Now we can find the desired numerical values. When F equals 2 newtons and 4 kg for m and 9.80 meter per second square for g, we get a equals 2 over 4 minus 9.8, which results in negative 9.40 meter per second square. If we denote the upward direction by plus and downward direction by minus, then we say that the object's acceleration is in the downward direction with magnitude 9.40 meter per second squared. When F equals 20 newtons, we have A equals 20 over 4 minus 9.8, which is calculated to be negative 4.80 meter per second square. So, since the result is negative, the object accelerates in the downward direction. And finally, when F equals 200 newtons, then we get A equals 200 over 4 minus 9.8, which is equal to 40.2 meter per second square. And since it is positive, then the object's acceleration is in the upward direction. Okay, we have answered all the questions in this problem. Then it is time to discuss the third problem. In this figure, there is a 12 Newton box resting on a horizontal surface. A horizontal force of constant magnitude F acts on the box. We are given the coefficient of static friction μs as 0.65 and that of kinetic friction μk as 0.44. The question is to find the frictional force on the box if F equals 5 newtons or 10 newtons. Okay, we are given W as 12 newtons, which is the weight of the object, coefficient of static friction, that is μs as 0.65, and coefficient of kinetic friction as 0.44. The free body diagram is drawn as follows. First, object is represented by a point. Second, the surface is represented by a straight line, and we call it x-axis. Then we draw y-axis perpendicular to the x-axis, that is, perpendicular to the surface. The first external force on the object, that is, gravitational force in the negative y direction, is drawn, and let's denote it by vector W. Due to this force perpendicular to the surface, the normal force denoted by N is formed antiparallel to W, and its magnitude is the same as vector W, which is the weight of the object given as 12 newtons. Next, the clearly seen external force, which is vector F, is drawn in the positive x-axis. So, from now on, we determine which type of frictional force acts on the object. As you remember from the lectures, magnitude of the static frictional force is the same as the magnitude of the net force parallel to the surface, provided that the magnitude of the net force is less than the maximum value of the static frictional force. Therefore, the first step is to calculate its maximum. maximum value of the static frictional force is found by the formula Fs max equals μs times n. If we put the values of the corresponding quantities into this formula, we get 0.65 times 12, which results in 7.80 newtons. Now, when F equals 5 newtons, and since it is less than Fs max, which is 7.80 newtons, then the frictional force, which is denoted by now small f, is found to be a type of static frictional force, and it is denoted by Fs, which is equal to the magnitude of the external force capital F, that is 5 newtons. Also, as discussed in the first problem, it is antiparallel to vector F. Namely, it is in the negative x-axis. Note also that the object does not start to move, since the external force with magnitude of 5 newtons is less than the maximum value of the static frictional force, that is 5 is less than 7.8 newtons. In the second case, namely when F equals 10 newtons, then it is greater than Fs max, which is 7.8 newtons. Therefore, we use the formula for the kinetic frictional force, which is given by small f equals Fk equals mu k times capital N. If we substitute the values of them, that is 0.44 for mu k and 12 newtons for N. Therefore, we obtain 5.28 newtons. Again, it is in the opposite direction of vector F, namely in the negative x direction. As a conclusion, since the magnitude of the net force F net is equal to 10 minus 5.28, that is 4.72 newtons, the object moves to the right. Alright, we have answered all the questions well in this problem, and it is time to solve another problem.